We'll consider an example here of a falling rock with an air resistance. We're going to have a 150-gram rock dropping from a bridge. If the bridge is 100-meter high and the air resistance removes 67.0 joules during its fall, the question will be with what speed does the rock hit the water below? We will need the ground. I can choose whatever I want. A convenient and natural choice is to place the ground at the level of the water. That means the original vertical elevation will be that original height, 100 meters, or the height of the bridge. With that, I can actually look at the total mechanical energy at the top. Kinetic plus potential will give me 1/2 mv squared plus mgh. Of course, if the rock is being dropped from the bridge, that implies that it starts with 0 speed, so I can just ignore this term, and I can see that the total mechanical energy at the top will come from the potential energy. At the bottom location, at the level of the water, kinetic plus potential will give us 1/2 mv squared plus mgh, but there the height will be 0 because of our choice. So I'm going to ignore this term, and I'll see that the total mechanical energy there will be simply equal to whatever the kinetic energy of the rock is, 1/2 mv squared. Here v is the speed at the ground, the bottom level. The work-energy relation or theorem sets that any changes in the energy are due to the work of non-conservative forces. In our problem here, the non-conservative force will be the air resistance. The only other force here is gravity, and that is a conservative force. Remember, conservative forces are forces with which we have associated potential energies, and in mechanics, there are only two forces, generally speaking, to worry about, to be considered conservative. That's gravity and elastic force of a spring. So let's go back to that work-energy relation. We're going to have the difference between the mechanical energy at the bottom and the top, bottom being our final position and the top our original position, has to be equal to the work of the air resistance. In other words, 1/2 mv squared at the bottom minus mgh naught, which is the height at the top, has to be equal to minus 67.0 joules. I put it minus here because the problem tells us that the air resistance removes 67 joules. And in fact, we all know that air resistance, just as friction, will always remove energy, mechanical energy, from our system. Numerically, with the values given in the problem, we're going to have 1/2 times the mass here, which I have converted into kilograms, 0.15 kilograms times the speed at the bottom squared, minus the mass, which is 0.15 kilograms times the gravitational acceleration, 9.8 meters per second squared, times the original height, 100 meters, that's the height of the bridge, and that has to be equal to minus 67 joules. In other words, the energy at the bottom will be less than the energy at the top by 67 joules. Which gives us, for the answer of this problem, that the speed with which the rock is going to hit the water will be 32.7 meters per second. If you want to practice, you can redo this example without their resistance. So there you'll have a conservation of energy, and your right hand side will be 0 there, and when you work out the problems with the numerical value, you should get for the speed with which the rock will hit the ground to be 44.3 meters per second.